continue the class while you or the repeatability of the producing the product for many times should give you some product which is a little bit different from others. So there is no two identical object which is, I mean, exactly identical. So they are the same or exactly the same to each other. There should be some variation, and this variation is not, you cannot notice. I mean, we cannot know that these two products are not the same, because the variation or the difference between these two products is or cannot be seen by normal eyes. I mean, it's very small. It's maybe in millimeter or in milli-inch or less than milli-inch. So usually they call it like the tolerance. So for example, if you have the product length, for example, should be 5 millimeter, and you have one product, the main dimension or the targeted dimension for this product is 5 millimeter, for example, for the length, 2 millimeter for the width, 1 millimeter for the height, and so on. So they are very small. There should be some differences in this, I mean, or variation which is allowed to, which will be allowed when they produce this product. So if this product is come like 5-inch 0.001, so still acceptable, for example. Otherwise, they need to reproduce this product. That means this product will be faulty product and they will throw it out, and they need to reproduce. For that, they make some margin for error. So they call it the tolerance, and usually this tolerance actually they define in the engineering drawings, and you can see in the example that we have, I mean, in the previous, in chapter 3, the different drawings, there is some values, we call it the tolerance, which define what is the margin of error which is allowed to be in this product, in this dimension. It's not about the total product. Sometimes this tolerance need to be defined for each dimension. For example, the height, the width, the length, and the diameter, and so on. Each dimension, it has its own tolerance. So there are different, I mean, for here, the tolerance, it's allowed for more part, because, I mean, if we have, sorry, if the tolerance here is more strict, I mean, the tolerance is very small, which is not give enough margin for error, that means most or the cost of this product will be very high. Why? Because if you make a small mistake in the dimensions, not you, I mean, not you, maybe you as a programmer, you are going only to write a program. So who will make this error? The machine itself, either the milling machine or the drilling machine or the turning machine. It will make this error because it's a machine. So machine, it has mechanical part, which is there is a vibration and there is rotation and so on. So it's not that much stable. So there should be some type of error in the product. For that, if this error within the defined margin of the tolerance, so it will be acceptable. Otherwise, they will count it as a, I mean, the faulty product, and they will throw it out and not use. For that, as the tolerance is very small, the product value or cost will be very high, because maybe they will produce 5 to 6 to 7 to 100 products in order to achieve this exactly product with the exact or defined dimensions for this product. So there is actually there is two organizations which make the standard for the products and for services in manufacturing. The one, they call it American National Standard Institute or American Society for Mechanical Engineer. They define some standards related to the tolerance values and related to the tolerance categories. And these standards used by the manufacturer or by the programmer or by the designer who make the sketch or drawings for the products for any during their design stage before they send to the manufacturing stage. So for according to this standard, they said each dimension should have tolerance except those dimension which is specifically identified either as a minimum value or a maximum value or as a reference point. So some of your dimension or some of the dimension, for example, for the product will be used as a reference. They will be used as a defined for maximum point, defined for minimum point. So this should be more strict about their values. So no variation should be defined for these parts. But other parts or other dimension, they should identify or define their tolerance. Okay. So as we can see here, we have three types of tolerance that used by this standard, and usually you can see this tolerance in your in the engineering drawings that is available either in chapter the slide for chapter 3 or also in the exercise. So this type of tolerance, the first they call it limit dimensions, the second unilateral, and the third is bilateral. So the limit dimensions here, they need to define some values which define the maximum and minimum value for these dimensions. So I mean the dimension should be within that within the defined range of this tolerance, no more, no less. So as you can see in this figure here, it looks like this one in the figure here for the tolerance. If you want to have I mean the limited or the limit dimension tolerance here, it will looks like this one. So on the top, for example, you have the biggest value, which is 0.980, for example, and the lowest on the bottom here is 0.975. That means the tolerance allowed for this dimension is the maximum value should be 0.98 and the minimum value is 0.975. So no more than these two, no more and no less than these two values. So these two values are stacked on top of each other. It looks like this one. I mean, in the figure, should be appear in this form. So we can see here. As you can see here, for example, this is we have these drawings and we have here 0.126 and 0.125. So this define what is the dimension or the length or the diameter of this cylinder, for example, or of this part. The dimension of these two parts should be maximum 0.126 and should be minimum 0.125. Cannot be 0.124, cannot be 0.127. Okay, so this is limit dimension. That means you define the limits for this dimension. So the dimension cannot be more than the maximum value and cannot be less than the minimum value of this tolerance. The second type here, they call it unilateral tolerance. And the unilateral tolerance, they define the dimensions and they put plus minus. That means you have the dimension is 0.5, but you have plus minus 0.0 I mean plus 0.005 minus 0.000. That means in the case of the unilateral here, you are going to see only one dimension, which is, I mean, one tolerance, which is the positive or the highest value, while the other side will be 0.000. So this, they call it unilateral. So uni here come from only one dimension or one side, which is the upper value will be defined. So if your dimension is 0.5, that means the maximum value that you need to you can reach is 0.505, while the minimum value that you can reach 0.500 is the same, no minimum. The minimum is the dimension itself. The maximum is the dimension plus the maximum value, which is 0.005 here. Okay. The third type, and here, as you can see here, also the unilateral here, same you can see here. So you have 0.375. This is the dimension. You have plus 0.005, and minus here is our negative 0.000. So the minimum value is still the same as the value of the minimum value of the dimension is still the same as the targeted value, which is 0.375. But the maximum value can be, can allow for error for 0.005 plus. That means you can, this value can become 0.380. So it has 0.005 value as the maximum or upper value variation according to the unilateral standard. The third type, which is a bilateral hair, and the bi hair, it's come from the two directions. So it's allowed upper value and lower value of tolerance. So you have a maximum, you have the dimension, plus the dimension, you have some range to change. Uh, I mean, upper, less than the dimension, also you have some range to change. So for example, here you have 1.170 plus minus 0.002. That means that this dimension can be changed, or this diameter can be changed from 1.172 to 1.168. So it gives you a margin for change for this dimension. And actually, this margin or this tolerance will be fed to the machine, so the machine will not make a big margin than that values. It will be allowed. Other than that, the product or the produced object will be count as failed object or not correct object, so they cannot be count as a good finished object or a final object. Okay, so this is bilateral here. You can see in the figure for the case of sorry. So in the case of the bilateral hair, this is the uni, and in the case of the bi, you are going to have plus minus of these two values. So 0.002 for the upper and minus 0.002 for the bottom values. Sometimes none of these tolerance will be provided in the dimensions. As we said, these three types of tolerance that we talk here, these three types should be attached to the drawing. So as you can see here, this dimension has tolerance. This dimension has tolerance. This diameter has tolerance. That diameter has tolerance. For each dimension on the figure, for example, here you have here, there is a tolerance here for unilateral, and you have here the limit dimensions. The limit dimension tolerance. So each dimension in the drawings should have its own tolerance. But in the case there is no tolerance for each dimension, they used to define something, they call it general tolerance. And the general tolerance here will be applicable for the whole engineering drawings. Drawings, all tolerance will be applicable for the same. Where is this one? Okay, so, and they call it this general tolerance. So general tolerance here defined based on the dimension values. For example, if your dimensions consist of one digit or one decimal digit here, like 1.2, 1.5, 6.7, 3.9, just one decimal after the decimal point. You have one digit after the decimal point. So they make its tolerance is, for example, plus minus 0.02, for example. So this any dimension in the drawing which consists of 1 point something or 2 point something, just one decimal point after that, one digit number after the decimal point, so it will has tolerance of 0.020, for example, plus minus, or like by the bilateral tolerance, for example. Any angle, for example, it will has like 0.5. So this will be applicable for all angles in the drawings, and this will be applicable for all dimensions which has one digit, for example. If you have the dimension is 1.23, 1.56, 1.78, so, or 5.29, whatever is the number, but it has two digits after the decimal point, so its tolerance will be 0.010, for example, plus minus. Each dimension which consists of or which include three digits after the decimal point, for example, it has tolerance of plus minus 0.005. This is not fixed. This number can be changed, but the idea here, this tolerance will be applicable for all dimensions which consist from three digits after the decimal point. And this tolerance will be applicable for all dimensions which consist of two digits after the decimal point. This tolerance will be applicable for all dimension which has one digit after the decimal point. This tolerance will be applicable for all angles or all dimension of angles and so on. Okay, so this we call it the general tolerance. So as you can see here, for example, if they gave you this type of tolerance, they said any number with one digit is tolerance is plus minus 0.020. So you can find the dimension which is consists from one digit, for example, and you add the tolerance of 0.02. So if you have this 2.68, so directly you are going to apply this tolerance. If you have this 3.435, directly you are going to apply this tolerance. That means it will allow for plus 0.005 minus 0.005 and so on. So each, each angle that you have, you are going to apply the angle tolerance that will be provided as a general tolerance. Represent the total amount or the total value that allowed to be changed from or varies from the targeted dimension. So for example, here this targeted dimension is 0.5 inch or 0.5 millimeter or 0.5 centimeter, whatever is the unit. So this is our target, and this dimension, it has two it has bilateral plus minus 0.1, for example, plus minus 0.01. Okay, so the tolerance here is bilateral, it's plus minus 0.010. And for in this case, you have 0.01 on the less side or on the minimum or on the bottom of the target value, and you have 0.01 on the maximum side or the top or greater than the targeted value. So here is less than, here is greater than. So 0.01 plus 0.01, it will give you 0.02, which is the total tolerance allowed for these drums. Okay, is it clear till here for tolerance? This slide is defined the total tolerance, and the total tolerance here is the value that describes the maximum amount of variation within the whole it's like the whole range. So from the minimum value to the maximum value. If it is bilateral here, so for example, you have plus minus 0.01. So in this case, what will be the total value from the minimum value of the dimension to the maximum value of the direction? So this is the target value is 0.5, but what is the minimum value of the direction? It will be 0.5 minus 0.01, so it becomes 0.49. What is the maximum value allowed for this dimension, or the maximum length of this dimension? It will be 0.510, because you are going to have 0.5 plus 0.01. So the total is, the maximum is 0.51. So the range from the maximum value to the minimum, the maximum allowed value or allowable value here to the minimum allowable value for this dimension, we call it the total tolerance. So here the range from maximum value, which is 0.5, if you make 0.51 minus 0.49, it will give you 0.2, which is the maximum tolerance. But if this one, for example, is plus minus, like plus 0.1 minus 0, like we said before, it is like unilateral. So it's not like plus minus here. It becomes the tolerance is like this one. The tolerance in this case like 0.1 only plus, and for the minus is 0.000, like we said before, it is like 0.000. So in this case, this maximum, the case of the total tolerance in this case will be only 0.01. It's not 0.02, because the maximum value will be 0.51. The minimum value will be 0.5, no more 0.49, because we have only unilateral tolerance here. So this will be the total tolerance for this case. For the one that we talk here, which is like one digit is 0.02, two digit is 0.01, three digit is 0.005. This when we talk about the general tolerance, okay? So that means in the case that you already have a tolerance, how to find the whatever is the value, is it 0.1, is it 0.2, is it 0.005, maybe 0.003, these not fixed values. These tolerance value are not fixed, but this is like example how we define the general tolerance for the whole dimensions in this figure. Instead of define tolerance for this value, tolerance for this dimension, tolerance for that dimension, tolerance for that dimension, they used to have something, they call it general tolerance. So they define it either, sometimes they put it in the figure. If you remember last time, wait, in the last lecture here, sometimes they write the tolerance in this slide here, on this block here. This one you can see tolerance plus minus 0.5 millimeter. That means this one is 0.5 millimeter plus minus 0.5 millimeter will be applicable for all dimensions here. For that we call it general. It doesn't mean that it should be one digit 0.2, two digit 0.5. No, it's not like fixed value. This thing the designer will define for his drawings, if he don't want to highlight the dimension or the tolerance for each part here. But in the case that you have a tolerance already defined, like we have here, in this slide here, of the total tolerance, the tolerance already defined. It's not a general here. It's defined for this dimension only. Whatever is this dimension is 2 digit, this dimension is 3 digit, we don't know. I mean, we don't care. Our tolerance already given is plus minus 0.01. So this tolerance, the type of this tolerance is bilateral because we have plus minus two values as the same as that one here that we have here. The same 1.17 plus minus 0.002, for example. Since you have plus minus two the same values, so this we call it a bilateral. If you have only one dimension plus but the minus is 0, so this we call it unilateral. And when we have it for each dimension, as you can see here in this figure, how many tolerance do we have? We have two. We have here unit tolerance and we have here the limited tolerance. So we define for each dimension its own tolerance. But in the case of the general tolerance, no need to define for each dimension. We just define general tolerance for all. So I can change this one to 0.03. I can put it 0.05. Depends on the product or the object requirement. What is the allowed error in the dimension or the allowed variation in the dimensions. So in this case here, the tolerance already given is the tolerance already given is bilateral, which is 0.01. It's not general here because this dimension, I mean tolerance defined for this part, for example. So our targeted is 0.5, but we have plus minus. So minus, that means it will give you 0.49, plus will give you 0.51. So what is the total range from maximum value of the dimension? This the maximum. If the product has a length of or a dimension, if this dimension that we produce has like 515, so in this case this product or this object is not acceptable, so they will throw it. They will not package and send to the customer, or they will not put it in the machine to build the machine, or they will not put it in other product or other manufacturer product, because this is not acceptable, because it has value which is more than the acceptable error or the acceptable variation in the product length. So this is the maximum value, which is 0.51. Here is the minimum value, which is 0.49. So if the product in the, I mean, what will be the total tolerance? It is the value, or what is the distance or the length or the interval from the minimum to the maximum. So what is the variation here? It will be 0.02. to 0. Plus 0.1 plus 0.1, so it's become 0.2. Don't say plus 0.1 minus, it will be 0. No, it is like this one. It's like a distance here. We are talking about the length. So what is the total tolerance for these dimensions? It is 0.02. It's not the general tolerance. It is not the unilateral or bilateral. We call it the total tolerance. Okay.
Okay.
Okay. Is the tolerance is 0.1? What is the total tolerance? Plus minus. If it is plus minus 0.1, so the total tolerance will be 0.2. If the tolerance is plus minus 0.3, so the total tolerance will be 0.6. It's like this one. It's just what is the allowed or the interval or the total dimension, the total value of error that will be allowed within this value. Okay. Clear?
Yes, sir.
Yes, sir.
So you have this question in the quiz. So please you should understand.
Sir,
Yes, yes.
if the bilateral and limit tolerance is the same, right?
Which
The total-
one? No. You are talking about the total.
Yeah.
Okay. So for the unilateral here, for the limit, the total tolerance here, for example, if I ask you now, what is the total tolerance for this part? 0.126 minus 0.125. This is the maximum value. This is the minimum value that allowed. So it will be like 0.001, correct?
Yes.
So this is the total tolerance. For this case, the total tolerance here will be what? 0.005. Okay?
Five.
Yeah. Right.
Okay. Another parameter or another aspect of the electrical drawing or of the blueprint of the CNC drawings here. They call it the thread and fastener. So the thread here is more related to when we talk about the controller for the, the drive. When we talk about the drive controller, the servo motor, and the thread screw page, and so on. So all this, when we want to represent the thread in the drawings, because the thread is important in the machining, so always you have some hole, drill to make, some bolts to have screw and so on. So the screw thread here actually is rarely or seldom provided in the drawings. Why? Because it's very complicated. It's not easy to represent such thread in the engineering drawing, but still have some way to represent this thread in the engineering drawings. So how to represent? There are three methods actually, either pictorial or schematic method or simplified presentation. So for pictorial and schematic method here, it gives like more details than the simplified presentation of the thread. So sometimes here, as you can see in this figure here, we have the first one is the pictorial. So the pictorial will give like image for or like real representation for the thread. So you can see here, if you see this one, you will understand this is a thread. This has this how fast the the angles here will be changed for the thread, how many teeth for this thread, and so on. So it gives you more like isometric view or like a picture for overview of this thread. So it's become easy to readable. You can read it. You can understand how the nature of the thread, but also it's difficult for the designer to draw all these lines with specific angles, with specific dimension, and so on, to represent either the external thread or the internal thread, either the external part or the internal part of this thread. For the schematic representation, also it uses a lot of lines here to draw, either to represent the diameter, to represent the teeth of the thread, to represent the step or the pitch of the thread. But also, more details, but it's not, this looks more real or more similar to the actual thread, which is the pictorial representation. Here is more schematic, so just drawings. So maybe count how many threads, what is the angle of the thread, what is the diameter of the screw, and so on. So they call it the schematic representation. In the third representation, which is the simplified representation here, so in the simplified, just you have like an overview, like cross-sectional of the thread, like the cross-sectional view that we learned before, or the parts, projection of the view either from the side or from the top and so on. So it has more simplified, there is no lot of lines like we have in the previous two representation of the thread. Usually for for that they said it's rarely represented in the drawing, but there is. Sometimes they need, if they want to represent some of the screw for the drilling machines and so on, so they need to have some representation to know the dimension, the length of the screw, how many teeth, what is the angle, and so on. So there are some parameters about the thread they need to define when they make this blueprint for the products. So as we can see here, this is the zooming for this representation here for the thread. So you can see they need to define these angles, for example. They call it the thread angle. They need to define what is the length of each of these lines. What is the round? How is round like this one? So you can see it's not just normal angle, it's angle with some straight lines here. There is how many threads, how many threads per 1 inch, for example, how many threads per here they need to define, for example, the root. The side is more right with right angle, or the side with specific angle here. So many of the details, the pitch, for example, here, what is the pitch for these threads, the one that we use in the calculation, for example, for the screw of the drive, the servo motor and so on. This either internal or external representation of the thread, it gives more details about this thread, and these details or this calculation will be used to feed to the drilling machine, for example, to the milling machine, turning machine, in order to create specific details or specific feature for this drill based on its the requirement to fix. Usually they use such screw and so on to fix some to fix the element, to fix two bars or two objects to each other and so on. So they use this representation to define this thread. So these are the parameters that they need to define. For example, they need to know the diameter of the thread, number of threads per inch, thread series, either national. Actually, there is some standard for the thread series. How it looks like the zigzag here for the thread, either national chorus, national fine, national extra fine, and so on. So all these parameters based on the standard they need to define. They need to define also the class of feet for angling for the loss, for example. It's more, to achieve a finished product. The finished product, that means without any extra piece on this part, without any error in these dimensions between the thread or between the steps of the thread here, with the angle of this thread and so on. So all these usually defined in the standard of this, the standard that we mentioned before for the American Institute standard for manufacturing and surfaces. So here also, this is in the case of the second representation. This one is actually more related to the pictorial representation, as we can see here. So in the pictorial representation, we said is more practical or more real, looks like a more real product. So when we have this zooming for this part, it's become more clearer how they represent for this thread. And the second here, when they use the schematic one, the schematic representation, and it shows us the as a line, as a number here. So they need to define this also the same parameter, the class of feed, the thread series, number of thread per inch, the diameter of thread, and so on. So this only the value that will be fed to the machines. So for example, there is some code here like G something. So this G code or N code will include such parameter, and the machine will understand there is some specific standard to define these dimensions. So for that, in the microcontroller of the CNC machine will understand this one is represent the diameter, so it will make the diameter of the thread 2.5. This one is represent the thread per inch. That means there is 13 thread per 1 inch. So after 1 inch, it will repeat again 13 thread, for example. This is the thread series, the type of the thread series. There are different type of thread series defined in the standard. So already fit to the microcontroller, for example, and already known by the programmer. So this will be defined according to the thread series. Also the class of fit and so on. Same here for the left hand or thread of notification, the same for this, the previous one. They need to define all these parameters, thread series, number of threads, and so on. So this is just some of the features or readings which can be extracted from the drawings and then included in the program that will be fed to the machine for either for any task the machine is required to perform, either for drilling or for milling and so on. The last feature, which is they call it the surface finish, and the surface finish symbol here. When we say surface finish, that means we already have our object or our product, but at the end need to improve either the surface. I mean, is it smooth or hard? The surface of this one, we need to improve the geometry. For example, sometimes the product, it has like this right angle, how to remove this part to make it more I mean round angle here or round end. If the surface is somehow there is some bars on the surface still need to be removed, so we need to use the machine to remove this part to make it very small. Depends on what is the type of the material that we use to produce our product, or is it wood, is it aluminum, is it plastic, is it metal, steel, and so on. So it depends on the material and it depends on the requirement for the product. So when we say surface finish here, there is a symbol for surface finish. It shows what is the degree of smoothness of the surface. Is it very smooth? Is it hard? Is it medium? And so on. So there is a table to define based on the inch, or the measurement in inch or in nanometer, in micrometer or nanometer, and so on. So these values will be considered during the feeding of the program. So there is a number will be added here to the surface finish symbol, which is a surface finish symbol here. They add some number on this part, and this number will define how the roughness or the smoothness of the surface. Okay, this value will be either in micro inch, in milli, or also in inch. Depends on what are the measurement which used to the product, and depends on how big is our object. The number also may be written above on the horizontal extension of the symbol here to design the maximum waveness height. This is another parameter that need to be designed or to be added in order to define the surface finish symbol. So as you can see here, this will be the surface finish symbol here. And this number which represent the value of roughness or smoothness of the system, of the surface. So for example, 16, how many 16 inch or 16 milli inch or 16 micro inch depends on the table that we have. So some are very smooth, medium, hard, and so on. So the symbol here used to indicate the surface finish are shown in this figure here according to the standard. So this is the value for the surface. I mean the roughness height. This is the waveness. It will be represented in this part, and here also another values of the waveness. The table that we have, we focus on this part only. Okay. So the table we have in this chapter, at the end of this chapter, is give you the roughness height of this surface for the finished symbol. So as you can see here, so these values are in micro inch. So if the surface finish is 1000, that means it is extremely rough. If the surface finish is, for example, 125, that means it is average smooth. If the surface finish is 63, as we see here, for example, this is 63 in this surface, for example, so this value means better than average finish. So I mean, this is the fine finish, this is the very fine finish, and so on. So this some terms which is defined for manufacturer, designer, so they know based on the what is the project, I mean what is the object that they want to produce, and what will be the material that they are going to use for finishing this product. Okay, so here we define the, I mean they define the micro inches, I mean the values or the code or the number that will be used in the surface finish symbol. Here we have the definition or the type of the surface, and here when we need to use this type of surface. For example, the 500 here used where stress requirement and close tolerance are not required. This one is used for close fits, for stress path, and so on. I mean, depends on the object, depends on the material that will be used for produce this object. I think this chapter only more on the, I mean, give you an idea how as engineer they can include all the details about their design part or design object in order to be readable or understandable by the people who will produce. Because the people or the engineer who makes these drawings or engineering drawings or blueprint are not the same as the people who will produce the product. So they do their drawings, maybe also other company who make the drawings for this product, because usually for in manufacturing and so on, either other company or other department, so they make their own design product or they design sketch or drawings, then they send it to the manufacturing department, for example, and the people in the manufacturing department need to create the program to convert or to guide the machine to finish this product or to produce this product. So in order to make these drawings are readable or understandable by the engineer, so they make it like there is some standard form, there is standard terms, standard definitions. They need to define for each part. As I told you, there are many of these standard forms or standard features that they need to include in their drawings. I mean, sometimes they need to define for the each part in the drawing, it has its own standard term and definitions. Like for example, when we talk about the dimension of the line, it's not the same as when we talk about the dimension of the circle, for example, or about the dimension of the hole. So it's each part or each type of drawings. I mean the drawings with the right angle is not the same as the drawing with the round terminal. Okay, so I mean each type of this drawing, it has its own standard, and usually the designer make the drawing, just send it to the programmer do their task to translate these drawings into code. Then they send this code to the controller of the machine will perform the task based on the feed values or this dimension with this tolerance, with this surface finish, with this thread Fitner and so on. I mean, so it will be understood by the machines to perform this task with a minimum value of errors.